The Antarctic ozone hole is an annual springtime event above Earth's frozen, southernmost continent. Conditions above Antarctica magnify the destructive potential of a changing atmosphere. Naturally occurring polar stratospheric clouds, man-made CFCs, and the return of sunlight set off a destructive chain reaction that decimates huge portions of the ozone layer, a critical protection to life on Earth. Stratospheric ozone is necessary because it blocks harmful UV radiation given off by the sun, a primary cause of skin cancer and cell damage in plants and animals. Throughout the 20th century, production of chlorofluorocarbons, or CFCs, were manufactured as a safe, non-toxic replacement for use in refrigeration, air conditioning, and as a propellant in aerosol cans. Growth in CFC use took off worldwide with peak production of over 1 million metric tons per year. But whereas CFCs are safe and inert in the lower atmosphere, they do undergo significant reactions in the stratosphere, where they are exposed to powerful ultraviolet radiation not seen at the surface. Scientists began to notice a springtime depletion of stratospheric ozone and in 1974 linked it to the chlorine in CFCs. In the early 80s, the depletion increased dramatically and the need for controlling CFCs became urgent. In 1987, 27 nations signed the Montreal Protocol to reduce substances that deplete the ozone layer. A further worsening of the ozone depletion was avoided, but natural processes remove CFCs at a very slow rate. Continued monitoring of our atmosphere, the ozone layer, and the annual Antarctic ozone hole need to continue. The South Pole is an ideal location to do this. The Amundsen Scott South Pole Station was built at 9,300 feet above sea level, on top of the Antarctic ice sheet. The site has been continuously occupied since 1956 and is an ideal location for many scientific observations. NOAA's Atmospheric Research Observatory, located in the protected clean air sector, measures the cleanest air on Earth. For over 30 years, NOAA scientists have launched balloons from the South Pole to monitor the ozone layer. The balloons rise to over 100,000 feet and collect high-resolution data about the ozone layer. Because of its location at Earth's southern axis, South Pole experiences only one sunrise and one sunset per year. As the Earth orbits around the Sun, the two equinoxes mark sunrise and sunset at the poles. When the sun finally sets after 6 months of day, 6 long, cold months of night begin. Without sunlight, it gets very cold. In the darkness of winter, wind patterns stabilize around Antarctica, preventing warm air from mixing in. This barrier allows the cold air over the continent to get even colder. This is the Antarctic polar vortex, a key component in the process leading to massive ozone destruction. Because of the Antarctic polar vortex, stratospheric air temperatures above Antarctica can plunge well below negative 80 degrees centigrade during the winter. Polar stratospheric clouds form only at these extremely cold temperatures. Let us imagine an ice crystal formed in a polar stratospheric cloud. Reactions in polar stratospheric clouds perform two functions critical to ozone destruction. Stable reservoirs of chlorine in our atmosphere combine on the crystalline surface to release molecular chlorine. The molecules with the ability to restabilize chlorine remain stuck to the ice crystals. In the cold, dark conditions above Antarctica, ice crystals begin to settle out, removing themselves from the destructive chlorine molecules now present in the ozone layer. High above Antarctica, weeks before sunrise will even reach the South Pole, energetic photons from the sun begin to strike the molecular chlorine within the vortex and kick off the process of destroying the ozone layer. Chlorine-free radicals destroy ozone. The resulting molecules bond together, but they are weak and easily broken. Light from the rising sun is strong enough to re-release the chlorine atoms, allowing them to destroy even more ozone. And the catalytic cycle repeats itself. Each chlorine atom can destroy thousands upon thousands of ozone molecules. Chlorine, in a similar reaction with bromine, completely wipe out entire sections of the ozone layer. Throughout August, September, and October, while the vortex remains strong, chlorine completely decimates the ozone layer and the Antarctic ozone hole fully forms. Eventually, the vortex breaks apart, and molecules with the ability to stabilize free chlorine mix back in, along with ozone from the mid-latitudes. The Antarctic ozone hole fills back in, until next year.